Okay, welcome back. So we now have another set of papers about the economics of climate change. We'll have 3 papers and then questions again at the end. First paper presented by Professor Hill from Columbia University. It will be about an important challenge, the challenge of accounting for ambiguity models in climate change literature. Professor Hill is coordinating lead author of one chapter of IPCC, as also Professor Kolstad, who is going to talk after Professor Hill. Professor Kolstad from Stanford University, who is going to talk about uncertainty in mitigation and also adaptation, which has not been so much developed so far in economics. And then we'll end this session with a presentation by Professor Pindyck from MIT. Professor Pindyck has written a set of very influential papers about the economics of catastrophes, and I guess he will present a summary of his contribution to this literature.
Thanks. So this, as you can see, is joint work with Anthony Milner of London School of Economics. So I'm talking about uncertainty, clearly, taking a slightly different tack from what you've heard so far. I want to spend much of my time describing the sources and the nature of uncertainty in the area of climate change. Why are we uncertain? What are we uncertain about? What are the major sources of uncertainty? And then I'm going to talk about the implications of the conclusions that emerge from that for the way in which we make decisions about in the context of climate policy or insurance under climate change. So, as we all know, climate is changing, that's definite, but it's about the only thing that is definite in this area. The basic physical principles of climate change are clear, but exactly what these imply in terms of the way the climate will change and how fast it will change is not at all certain. So we've got considerable scientific uncertainty about the nature of the future climate. We've also got a lot of what we call socio-economic uncertainty, because even if we knew exactly what the future path of climate would be, there'd be a lot of uncertainty about its social and economic consequences. We heard some discussion earlier today about the so-called damage function, which is the function that tells us how climate affects economic activity. That's actually a very under-researched field. We really don't have a very profound understanding of how economic and social activity would be changed in a world where global mean surface temperature had gone up by 3 or 4 degrees. So that's what we call socio-economic uncertainty. Now, it's common to sort of decompose scientific uncertainty into these 3 components you can see up here. And indeed, you heard this from Valerie in the first session yesterday, talking from a more scientific perspective. Scientists distinguish between internal variability, modeling uncertainty, and emissions pathway uncertainty. Internal variability arises because climate models are very complex nonlinear models. And complex nonlinear models tend to behave chaotically, which means they show very, very sensitive dependence on the way you specify their initial conditions. So a small error in the specification of exactly where we're starting the model from can actually lead to quite a big change in the outcome 50 or 100 years ahead. And that's what's called internal variability. I don't quite know where that phrase arises from, but that's the scientific word using it. Then, of course, there's obviously modeling uncertainty. We don't know exactly what the right model is. We understand the laws of physics, and we're fairly clear about those. But the laws of physics operating at a global scale are far too complicated to model exactly and precisely. So different people make different approximations to them. And there are lots of different climate models out there, and they're all essentially embodying the same laws of physics, obviously, but they're approximating them in different ways in order to make the outcomes computable. So there's modeling uncertainty. And then finally, obviously, the whole process is driven by the level of emissions. If you want to make a forecast of what the climate will be in 2100, you need to make some assumptions about the time path of emissions from now to then. And that is also very uncertain indeed. So those are the 3 categories of uncertainty that scientists recognize. When it comes to socioeconomic uncertainty, we can distinguish maybe 2 categories. There's sort of what we call positive or empirical uncertainty and normative uncertainty. Positive or empirical uncertainty just arises for the same kind of reasons as you have model uncertainty in the scientific context. That is to say, we don't really understand the relationship between climate and economic activity. There's an awful lot of work being done on that at the moment, but it's still a long way to go before we have a convincing set of models of how climate affects various aspects of economic activity. So that's what I'm calling here the positive or empirical uncertainty. I mean, I really can't tell you as an economist what the economic consequences would be of a 3.5 degree increase in global mean surface temperature by the year 2050, just to take a concrete example. I know that there's various estimates of that, but the variance of these estimates is really quite large. So that's the sort of the positive or empirical uncertainty in the economic context. There's also in economics another source of uncertainty which you don't have in the scientific world, which we've called here normative uncertainty. And this arises from disagreements about some of the key parameters that you put into the sort of integrated assessment model, for example, that Simon was talking about earlier. In one of those integrated assessment models that you run, there's two parameters which are quite important parameters, which are not empirically determined. They're the discount rate, and you've heard some discussion of the discount rate so far, and there's been a lot of debate amongst economists as to what is the appropriate discount rate for discounting benefits in the very, very far distant future. And it makes a huge difference. You know, the sort of economics of climate change is radically different at a zero discount rate or a very low discount rate, as, for example, in the Stern Review, versus at a 5% discount rate, which is the kind of number that someone like Bill Nordhaus has occasionally used. And policies that look attractive at a low discount rate are very unattractive at a high discount rate. So this is a debate which has a big impact. And in fact, a small change in the discount rate has more impact on the outcome than a small change in equilibrium climate sensitivity, which is the key physical parameter in this game. There's also a less visible and less widely debated parameter called the elasticity of the margin utility. It's a rather untransparent phrase, and I won't elaborate on it too much more, but it's essentially a parameter which captures your preferences for equality versus inequality. And that turns out also to be quite an important parameter in climate models. I mean, Simon made a standard assumption about that and didn't highlight it very much, but I'm sure if he changed that parameter, his results would have looked somewhat different. Those are the basic sources of uncertainty. As I said, you've got these three sources of scientific uncertainty: internal variability, model uncertainty, emissions pathway uncertainty. Then you've got these two types of socioeconomic uncertainty, again, model uncertainty, empirical uncertainty, and this uncertainty arising from disagreements about the appropriate values of parameters, which are essentially ethical in nature. Now, what I'm going to do next is spend a little bit of time talking about this diagram. But before I get to that diagram, let me tell you a little bit about what it is. I'm going to be talking about the estimates of the value of the equilibrium climate sensitivity, or climate sensitivity as Simon called it a few minutes ago. And what this is it's a number which tells you the change in global mean surface temperature in the long run in response to an impulse doubling of the concentration of CO2. Okay, so there's a thought experiment here. You double the concentration of CO2, you let the climate run forward, and you see by how much the temperature has increased in the long run. Okay, and Simon showed you a diagram which he took from the IPCC, which basically suggests that the equilibrium climate sensitivity is most likely to be somewhere between 2 and 4 degrees centigrade. So that's saying that in the long run, if you were to double the concentration of CO2 in the atmosphere tomorrow, then in the long run, the response to that would be something like a 2 to 4 degree increase in global mean surface temperature. Now, that's not a parameter that people feed into their models. Okay, that's a parameter which is estimated by climate models. And what this diagram does is it gives you 20 different estimates of the equilibrium climate sensitivity computed by 20 different modeling groups. There's 20 different modeling groups that are involved in something called the Climate Model Intercomparison Project, CMIP. Here, each of those models has been run 10,000 times in a Monte Carlo simulation to try to generate a probability density function over the value of the equilibrium climate sensitivity. So if we pick, for example, what's nice and visible, I guess this blue one is nice and visible. So this is just showing you one group's estimate of the value of one group's probability density function over values of the equilibrium climate sensitivity. So these guys are thinking that the most likely value of the equilibrium climate sensitivity is about 3.5 degrees, but there is virtually no chance it's less than 2, and there is some chance, if we follow this thing down, some significant chance it's as high as 5 or even 6. So I didn't mean to do that. So these are 20 different estimates of that type. As I said, you get them. These climate models are essentially underdetermined. There are almost as many parameters as there are observations that you can fit those parameters from. So the parameters, the way that they run the climate models is you run a climate model and you pick a set of parameters from a parameter space at random, and you rerun the model many different times with different random selections from the parameter space. So each of these PDFs, as I said, is generated by 10,000 runs of a particular model. And these numbers were put together by a co-author of mine on one of these papers, a guy called Miles Allen, who's a well-known climatologist at Oxford, and people in his group there. Now, what's interesting about this is that there is significant disagreement amongst the different modeling groups about the most likely value for the equilibrium climate sensitivity, about the distribution of possible values for the equilibrium climate sensitivity. And note, incidentally, that, and somebody said this yesterday, but I'll just repeat the fact that, pre-industrial concentrations of CO2 were roughly 280 parts per million. We're now at 400 and something parts per million. Current trends, we will double concentration of CO2 in the atmosphere by about 2060, so well within the lifetimes of plenty of people in this room here. So a doubling of CO2 is not something which is going to happen in the very, very long run. It's going to happen while you guys are alive. So we're talking about something which is not necessarily the very far distant future. So you can see that obviously the modes of most of these distributions are somewhere between 1 3/4 and 4 degrees. They're all somewhere in this range here, with possibly the exception of this purple curve here. That accounts for the diagram that Simon quoted from the IPCC, saying the most likely outcome was somewhere between 2 and 4 degrees. Remember that that's the mode. These are all right-skewed distributions, so the mean exceeds the mode, so the mean will be bigger than that for all of these distributions. But what is interesting is that there's a significant amount of probability out here at the sort of the 5 degree centigrade level. The general opinions that you're all very well aware is that, increases in temperature up to 2 degrees could be handled. I mean, they could have some serious consequences, but we could live with those. But that increases in temperature above 4 degrees would be very, very dangerous indeed for human societies as they exist at the moment. And there's even arguments that increases of 5 or 6 degrees could really throw a major block to the continuation of civilization as we know it. The famous figure that my climatologist friends like to quote is that when the global mean surface temperature was last 6 degrees less than it is at present, the northern US and most of northern Europe was covered by ice sheets a mile thick. When it was last 5 degrees hotter than it is today, there were no humans around at that point, but when it was last 5 degrees hotter than it is today, then there were palm trees and crocodiles at the North Pole, according to the fossil record. So a change of 5 degrees makes a radical change to the habitability of large parts of the Earth. From a climate policy perspective, it actually matters a lot how much weight you attach to outcomes in the sort of the 5 degree, 6 degree range. And we can see from this diagram that there are some modeling groups that are saying that the probability of a 5 degree increase is as high as 15%. Some saying it's as low as 1 or 2%. There's a wide range of disagreement over the likelihood of a 5 degree increase and the likelihood of a 6 degree increase too. Again, there are some people saying a 6 degree increase is a more than 10% probability, others saying that it's a vanishingly small probability. Now that's something which unfortunately is left out of the IPCC discussion on these. The IPCC reports tend to focus on the central tendencies, the means and the modes, and not on the tails. But from an economic perspective, and from a kind of policy-making perspective, and I think also from an insurance perspective, it's those outliers and the tails that are very, very important. If you're insuring against climate risk, you might really want to know whether there's a chance of an outcome as bad as this one here. If you're formulating climate policy, again, you might want to know whether there's a risk of an outcome as bad as this. And some of the main motivations for climate policy from a kind of economic perspective are to avoid really disastrous outcomes. So the probability of a disastrous outcome is really a very significant factor. As you saw from Simon's talk, what the IPCC did with this data here, and these runs were really done at the request of the IPCC, was to consolidate them into a single distribution. That's actually not what they should have done, to be quite frank. You've got a bunch of different distributions here. What you might think of doing if you're a statistician is to say, well, these are all different estimates of some true underlying distribution. So we'll try to derive what that true underlying distribution is by treating these as different estimates of it. Now that unfortunately isn't the case. First of all, there's no true underlying distribution. The equilibrium climate sensitivity is a number, not a distribution. But secondly, these are not independent estimates. Every one of these different models is calibrated off exactly the same data set, and every one of these different models reflects exactly the same laws of physics. The differences between them are really just in the way they're approximating the laws of physics and the way they're simplifying the models to make them computable, which are actually relatively minor differences to the models. My argument is that, and I'm going to make this point's going to be important, what I say later on, is that it's actually wrong to try to condense these into a single distribution. That we actually need to retain these and work with all of these. And I'll explain that by simplifying them into a single distribution, you lose a lot of important information. And in particular, you lose a lot of information about the range of opinions of truly disastrous outcomes in the 5-6 degree range. So I'll come back to that a little bit later on. Now here's another diagram which gives you some sense of the different types of uncertainty and their relative importance. I mentioned just now that there were 3 types of scientific uncertainty. Internal variability, which has to do with the chaotic structure of the models, the nonlinear structure of the models. Model uncertainty, which has to do with the way these models are specified, and emission pathway uncertainty. This is a diagram from a paper by Hawkins and Sutton, and you actually saw this yesterday in Valerie's talk, I think it was, which shows how important those 3 different sources of uncertainty are for different timetables. So it's essentially this is saying if you're looking at a timetable of, say, 20 to 30 years, then the most important form of uncertainty is model uncertainty, and also quite important is internal variability. But then as you go much further out, if you go to 50, 60, 70 years, and you're looking at the second half of the century, the total amount of uncertainty is dominated by uncertainty arising from the emissions pathway. And what we're showing here, incidentally, is this vertical axis goes from 0 to 100%. So we're normalizing to keep the total amount of uncertainty constant at 100%, although actually the total amount of uncertainty obviously is increasing exponentially as you go forward. But we're looking at the percentage of the total uncertainty here. And so what this is saying is that as you go forward, the percentage of total uncertainty is dominated by emission pathway uncertainty, uncertainty about what policies we will implement, if any, towards climate change, and that the internal variability shrinks essentially to 0, that model uncertainty shrinks, but not to 0 relative to the total. Another important point, and this is again very important from policy making, and I suspect from an insurance perspective too, is that uncertainties are very much a function of spatial scale. And the next couple of figure here shows disagreement between models as a function of their spatial scale. So let's look at the top left-hand diagram here. What this is showing on the horizontal axis, you've got spatial scale, going from 0, very small distances, to 10,000 kilometers, sort of continental scale, even above continental scale. And here you've got the intermodal spread in terms of the forecast of mean surface temperature, not global, regional surface temperature, intermodal spread in terms of degrees K. And what you can see, the different lines here correspond to different periods in the future. So the furthest into the future is the blue line, perhaps not surprisingly. And what you can see is that the disagreement between the models is relatively low at the scale of 10,000 kilometers, the continental or global scale, but increases very, very rapidly as you go to a smaller scale. And policymakers are really not that interested in the global mean surface temperature. They're interested in temperature in France, or temperature in Belgium, or temperature in the United Kingdom. And those are units that are measured more on a 1,000 kilometer scale than on a 10,000 kilometer scale. So to understand the degree of uncertainty, you really need to go to the left-hand end of these curves when you're looking at the kind of uncertainty that's relevant to policymakers. Again, if you're writing insurance policies, you're writing an insurance policy not on the global the global surface temperature. You're writing an insurance policy on what's going to happen in northern France or in southern Spain or some specific region like that. And the uncertainty about outcomes in that case is very much greater than the uncertainty about outcomes averaged over the globe as a whole. And the right-hand diagram here shows essentially the same thing, but for intermodal spread in terms of forecast of precipitation. Precipitation is generally much less well determined in these models, and you can see that the spread in precipitation increases hugely from 0.2 millimeters per day to 0.8 millimeters per day. So there's a fourfold increase in disagreement about precipitation as you go from the continental scale to the sub-country scale. So again, that's something which we don't hear a lot about, but it matters a lot because decisions essentially, as I said, are made at a local scale, a region, small scale, 1,000-kilometer scale, rather than at a global scale. And I've been involved in various exercises in the US trying to explain the consequences of climate change to individuals, to citizens. And again, what people want to know is, what will climate change mean for me and my region and my city, my part of the world? How will my part of the world look different in a 4-degree world than it does at present? And in order to answer that question, you have to come down to a very small scale. You have to downscale the models. You have to give climate forecasts, you give temperature forecasts, precipitation forecasts, humidity forecasts, and so on, that are relevant at the 100-mile scale rather than the 10,000-kilometer scale. And unfortunately, the uncertainty that you face when you look at the forecasts of different models on that scale is just enormous, and much bigger than the uncertainty you face when you look at global forecasts. And another, let me skip this guy, I'm running short on time. You get back to the issue of socioeconomic uncertainty. There really haven't been any serious attempts to quantify socioeconomic uncertainty. I mean, scientists are good. Scientists have recognized the sources of uncertainty in their models and done a lot to try to quantify and compare the different sources of uncertainty in their models. Unfortunately, there's been very, very little work trying to quantify different sources of socioeconomic uncertainty. There are a couple of papers in this area, but they're sufficiently rudimentary that I'm not quoting them here. But the important thing is that to realize is that one of the biggest sources of socioeconomic uncertainty, and this is something we saw in this diagram here, this is the emissions scenario uncertainty, which is a dominant source of uncertainty in climate forecasts going into the future. If you want to forecast emissions in the future, you have to forecast two things. One is human behavior, how different societies will respond to the threat of climate change, what will happen in Paris. We had a very pessimistic forecast on that yesterday from Jean, and I tended to agree with him. So you have to forecast human behavior, social behavior, and you also have to forecast technological change. Because obviously, if, to take a rather unlikely example, the problems of nuclear fusion were to be solved next year and would be offered low-cost, safe fusion reactors, then that would have a huge impact on the course of future emissions. So in forecasting future emissions, you're forecasting human behavior and you're forecasting technological change. And those are both notoriously difficult things to forecast, unfortunately. So there really is a lot of uncertainty in that field there. So what are the implications of this for decision making? I've got 4 minutes left, I notice, so I'm going to have to rush a little bit here. The implications for this for decision making, I think, this is the diagram you saw before, that actually there's two approaches to decision making in the context of uncertainty. One is to work with a kind of well-defined probability density function over possible outcomes. And that's the so-called expected utility approach. It's the one which is the default in economics. It's the one I teach all my students in my PhD courses in economic theory. And it dates to a guy called Leonard Savage, in a book called The Foundations of Statistics, which he published in 1953. The basis of that approach is an assumption that you can define a probability distribution over whatever you're interested in. It may be a subjective distribution rather than an objective distribution, but you can nevertheless do that. Alternative approach is to say, well, in many situations, we can't define the probability density function precisely. We have some kind of qualitative probabilistic information. For example, looking at this diagram here, we know that an outcome between 2 and 4 degrees is more likely than an outcome between 4 and 6 degrees, or an outcome between 0 and 2 degrees. But we can't really say on the basis of these distributions here exactly how much more likely the 2 to 4 degree outcome is than the 4 to 6 or the 6 to 8 degree outcome is. But we can rank them, nevertheless, in terms of likelihood. So we have some probabilistic information, but we don't have full probabilistic information in the sense of a well-defined density function. So there's a number of people who have worked on how do you make rational choices in that context. These are approaches which were generally called the multiple priors approaches. So they're approaches where you actually explicitly recognize that there are many probability density functions consistent with what you know, and you actually work with all of those rather than just trying to average them into one or selecting one as a preferred one. So that's the idea behind the multiple priors approach. And there's a couple of different approaches I'll just mention extremely briefly. One approach, which is due to two Israeli economists called Gilboa and Schmeidler, is based on the idea that you look at all of the probability density functions consistent with what you know. So in the case of, for example, equilibrium climate sensitivity, that would be all of these. You look at all the density functions consistent with what you know, and for each possible policy choice, you work out what the consequences of that policy choice are, the expected value, what the expected value of that policy choice is for each of the distributions. So if you've got 20 distributions for each policy choice, you work out 20 numbers. What's the expected value of this policy for each of the distributions? And then you assign to each policy the value, the lowest of all of those values. The worst, its value according to the least favorable distribution. And you essentially rank policies by those worst values. That's what's called max-min expected utility. And Gilboa and Schmeidler have a series of papers where they show that that actually does constitute rational behavior under certain definitions of rationality, which are very close to the ones used by Savage. They modify mildly one of the Savage axioms. Another approach, which is called smooth ambiguity, I'm not totally certain where that phrase came from. It doesn't seem anything obviously smooth or ambiguous either about it. But anyway, called smooth ambiguity is that we take all the priors that are consistent with what we know. We don't focus on the worst, as in the previous case. What we do is we weight them. So again, if we were to go back to this diagram here, we'd say we're going to work with all of these priors, and what we'll do is we'll calculate the expected value of a policy for each of these possible distributions here, and we'll put more weight on some distributions than others, and then we'll take an average. If we think that this is the best, if we think that this is the best research group, for example, we may want to give this distribution more weight than some of the others. If we think there's something very odd-looking indeed about this distribution here, which I think most people would do, then we'll give this one relatively little weight. So you can use some kind of subjective expert judgment to put relative weights on the distributions. You compute an expected value for your policies for each of these distributions, and then you take a weighted average of them. You take actually a weighted average through a concave function, to be absolutely exact. There's a couple of other approaches which are summarized in this table, but I don't think I've got time to go through those at this point, so I'll stop at that right there. Thank you.
Thank you, that was great. Okay, so here's the best disaster picture I could come up with. And this is the only picture you'll have in my talk. Economists are short on pictures compared to natural scientists. I just have three graphs here, though, to illustrate the kinds of uncertainty that Jeff was talking about. This is a nice one on that basically characterizes the price of consumer energy services in the United Kingdom. And this comes from an economic historian, and as you might imagine, going back to the 1700s to figure out the price of heating and lighting and transport is a little uncertain. But this is basically technological change that has occurred, and you can see there's been dramatic technological change, and it looks like there's no more change to occur in lighting, but of course if we magnify that, all of those graphs, there's projected technological change coming over the coming decades. And this is a infamous, I'll say, graph by McKinsey about the abatement cost curve for greenhouse gases and for 2030. And the main reason this is so controversial is, well, the reason it's controversial is all the negative costs. That's this, this area here, all these negative costs which sort of defy basic principles of economics and rationality. But the reason they're there is that they're talking about 2030 and they build in an optimistic estimate of technological change and other market developments. So it's not necessarily inconsistent with economic principles, but it's obvious that the amount of technological change, which is clearly unknown, is a major part of that graph. And here are three forecasts of future energy demand done by the U.S. Energy Information Administration. The one up in the upper right corner, or left corner, done in 1993, sorry. This one down the bottom, done in 2003, and this one done just a year or two ago. And if we look at the uncertainty about the different years, but focus on 2025, there's basically this is the socioeconomic uncertainty that Jeff was talking about. We have a great deal of difficulty knowing what the future is going to bring. Now, why is that relevant to climate change? Well, if we're trying to balance, if we're trying to look at how much mitigation we should invest in today, a fundamental issue is, well, how much should we invest in today versus waiting 5 years and investing even more then, or waiting 5 more years? Same problem we all have if we want to buy something like an electric car or energy efficient investment. The price is dropping or changing. When do we pull the trigger and make that investment? Okay, so let me move on to the themes of my talk. I'm going to talk about uncertainty as we're as this whole session is uncertainty, risk, and information. But I'm going to focus on private decisions. At the very end, I'll talk a little bit about policy decisions. But if you think about it, there are a lot of the focus in climate change is on what governments should do, what policies they should institute. But there are lots of private decisions, and that's particularly relevant for insurance, lots of private decisions, people that are subject to the changes in the climate that have to make decisions of their own, mostly about adaptation, but also about mitigation. If you're a firm that's a polluter, emitting carbon, then you have to make decisions about abatement, about process change, about capital investment that's going to have a lifetime of 20, 30 years. You have all these private decisions to make. So I'm going to focus on those, and for that reason, my talk is mostly going to be about adaptation. I'll have a little bit to say about mitigation as well, and what risks are privately insurable. And then I'll just close with a little bit on the implications of these uncertainties for policies, although Jeff has talked about some of what I had intended to talk about. So let me start by a little bit of taxonomy here. What I am talking about when we're talking about uncertainty and risk and things like that. Uncertainty is the simplest one. It pertains to the level of knowledge about a problem, either parametric uncertainty, we don't know what that one parameter is, the climate sensitivity, or structural uncertainty. We don't know how to model the evolution of an economy or an atmosphere. And then Frank Knight distinguished between risk and uncertainty, one being possible to establish a PDF or not. That's a distinction which I'm not going to concern with here. Then there's stochasticity, and these are random shocks that are generally unknowable. You think of a coin flip, and those are really different than something like the climate sensitivity, which, as Jeff said, has a true value. There is one number that is the climate sensitivity, at least if that simplification of the system is appropriate. It's just that we don't know it. It's not stochastic. It's very deterministic. It's just not known by us. That's distinguished from the weather or coin flips or other things the stochasticity that really is unpredictable, largely unpredictable. And I have a simple example here of the weather following just a simple process where Y is the weather, X is a bunch of explanatory variables, maybe just constants, and eta is a stochastic shock that determines the weather. Then we have, and we're getting more relevant to economics, we have asymmetric information where the one party knows more than another party, And a relevant example for climate change is the regulator will be less well informed about how easy it is for a firm to reduce its carbon emissions, and has to make regulatory decisions based on its level of information. The firm has better information. This basically, in the insurer context, is issues of moral hazard and adverse selection, which has a lot to do with whether these risks are insurable or not. Then we have abrupt change and irreversibilities. And without uncertainty, abrupt change and irreversibilities are not really an issue. If we know exactly where the thermohaline circulation is going to shut down, we just go right up to it and stop. Not a problem. The problem is we don't know where that is. And that's what makes abrupt change particularly dangerous. And the fact that what makes it even more dangerous is that we can't go back from it. Irreversibilities. Now, maybe some abrupt changes are reversible, but most of them are not. It's like walking up to a cliff. Once you go over it, you can't just back up a little bit, and except in the cartoons, and be at the top of the cliff again. And the Gulf Stream shutdown is an excellent example of that. And a lot of the abrupt changes that climatologists tell us about are of that character. And then there's learning, the process whereby uncertainty is reduced. And this is going to be particularly relevant for adaptation, because for private adaptation, the agent, the economic agent, the individual, the firm, needs to know that the climate has changed. You know, we talk about climate change, but we actually don't know whether the climate has changed or not, or how much it's changed. We think we know. We saw some probability density functions of the climate sensitivity. We think it's gone up by about a degree since pre-industrial times, but there's a lot of uncertainty in that. And the signal is very much disguised by the noise in this process. So that is going to be a major factor in the adaptation story I'll talk about. So in managing private risk, I'll just go through this really quickly because this is like bringing coals to Newcastle, I think. We have insurance markets, we have financial instruments where you can hedge price risk and things like their weather derivatives for hedging weather risks, although short-term weather risks. There are catastrophe bonds for countries. Mexico has used those, and others have used those to hedge some catastrophic risks. There are information market, prediction markets, which are not as popular as they once were, where information is essentially pooled by people buying and selling on both sides of that market and determining the consensus probability of events happening. Then there are real options, and in the climate area, I would put irrigation and air conditioning in that category. If you invest in air conditioning, you may not know that you're going to have a heat wave last weekend in Paris. Prior to that, you may not know it's going to occur, but you have air conditioning, it doesn't matter if it occurs. If it occurs, you use it. If it doesn't, you don't use it. Irrigation the same way. Okay, so let's talk about adaptation now. There are two basic types of adaptation, private or autonomous adaptation, and there are many synonyms for these words. I don't have all of them here, but private adaptation is things that are done by individuals or firms. They're done at the agent level in the economy or in society. So, farmers, everybody understands farmers because everybody has planted radishes when they were a kid, or everybody's been a farmer to a certain extent. So when I say farmers, that's a euphemism for all of the agents in an economy. Then there's public adaptation, and this is things like strengthening infrastructure, things that individual agents don't do typically, sometimes firms can do them. It can be part of a firm. If a firm owns electricity infrastructure, it's a vertically integrated electric utility, for instance, the firm can do it. But more often than not, this is public and is left to the public sector to take care of. Now, public adaptation is not necessarily going to occur automatically. It's a policy process, and in some in poorer countries, developing countries, public adaptation may run into real problems of incomplete financial markets. Private adaptation can have the same problem. But the main thing I'm going to assume here is that private adaptation happens automatically, but it depends on information. Okay, so key to the adaptation decisions are, as I will suggest, is uncertainty about the climate. Now, there are other things that are also important for adaptation decisions, uncertainty about technology and lots of other things, but the thing I want to focus on is uncertainty about the climate. It's relatively easy to adapt to the extent you can with full and complete information. You know, if I know exactly how much the climate's changed, I have a trajectory of how much it's going to change over the next 15 years, it's relatively easy to figure out what the appropriate adaptation is. I don't need insurance, there's no risk, I know what's going to happen. But in fact, if you're an individual, let's say you're a farmer, go back to the farmer metaphor, if you're a farmer, you may read the IPCC reports in your spare time, and you may know what the global mean temperature is, but you've just had a flood, and you're not quite sure if this flood is just the kind of flood you get all the time, or every 5-10 years, or if this is really a signal that the climate locally has shifted. The global mean temperature doesn't affect you, it's the local climate that affects you. So, and in fact, if you need to adapt, you're going to need to make investments based on what you think the change in the climate is, and you have very poor information about that. So optimal adaptation in the world of imperfect information means that you slowly learn about the true state of the climate. Remember, the climate has changed, or may have changed, but you just don't know it. And you're going to slowly learn what that true state of the climate is, and you're going to make what we could think of as errors along the path as you adjust to where you should be, as you adjust in the end to knowing what the true state of the climate is. So risk management tools can be important, but I want to focus on this informational part of this. So how do we learn? The standard way that one would anticipate a farmer, or actually individual people or firms learning about the climate, is to observe it, observe the weather. We don't observe the climate. And this is a simple model of learning about the climate that I introduced earlier. I'd like to look at it in a little more detail here. We're going to observe Y, and maybe we observe X, but we do not observe beta and eta. Eta is stochastic, that's the shock. Excuse me. So for instance, suppose beta is the climate sensitivity, eta is the weather shock, Y is the observed weather, and X is the greenhouse gas forcing. And we will learn slowly about beta. And we might think of our prior as based on the past 30 years of weather. In the United States, before climate change became an issue, climate was defined as the average weather over the previous 30 years by NOAA. Now you might, if you think it's going to change, you might change what your prior, but roughly speaking, that's what you'll do, and you'll slowly learn about it. So let me take you a little bit deeper into that problem of active learning about climate sensitivity. What the farmer knows is this expectation about the climate sensitivity, which is his best estimate of what it is. He also has a precision of it, which is just 1 over the standard error of it. And he bases it on what he's observed over the past 30 years, and every year he gets a new observation. The weather shocks arrive continuously, and he updates his prior. Now, you might say that this requires a farmer to actually run a regression or use Bayes' rule, but really it's just efficient processing of the information the farmer has. He can just take the 30 years of weather with his new observation, average them, and bingo, you've got something that would be equivalent to a efficient estimate of it. Ex ante, you expect precision of this estimate to increase. So if we consider an arbitrary firm using inputs X to produce output Y with weather W, so this is like a farmer. Farmer uses tractors, fertilizer, and weather to produce a crop Y. And we'll leave other factors out of this for the time being. But the farmer has to choose X, the inputs, based on the expectations about W over the growing season. So here in the Northern Hemisphere, think of yourself in April, where you're a farmer, you don't know whether it's going to be a hot summer, cold summer, or wet summer. You have expectations about that, but you have to make your planting decisions in April, most of them, and then see what happens. So your input choices depend on the expectations about it, and W has some distribution. The weather has some distribution with a mu and sigma squared, and that mu and sigma squared is your estimate of the climate. And your actual profits depend on the realized weather, your subjective estimate of climate, and other factors. So the realized weather comes after you've made your production decisions, so you don't, in fact, know whether you're going to get a good draw or a bad draw. So the resulting profits depend on your expectations of climate over the growing season. So this is the last line here, and the actual weather that's realized. So if, let me just skip through this quickly to the next graph in the interest of time. But basically, if we're uncertain about the weather, if we're uncertain about the climate, we don't truly know what the mean and variance is of the weather, and we're estimating it. That means we're going to have a bigger estimate of what the climate actually is. And we can then take this model of how a farmer would operate, and we can statistically estimate profits for a period of stable climate using real data, and we can estimate how the farmer actually, what the production function is, where its expectations of climate are known and weather is realized. We can then infer what happens if we shift the climate on the farmer. And we can measure the firm's response to a counterfactual of an unobserved climate. So just picture the farmer. We are experimenting with him, just like he's a rat in a laboratory. We're changing the climate on him. The poor farmer doesn't realize the climate has changed, and we're waiting to see how long it takes him to realize that flood keeps coming year after year, and he's got to change his behavior. And then we simulate what happens. So this a few graphs here to illustrate this. Suppose over time we take a piece of land as this value, and we subject it to a climate shock, unobserved climate shock. All of a sudden, the farmer is operating in less desirable climate, according to this anyway, and the value of output drops. And the farmer slowly keeps getting bad realizations on the weather, and slowly over time becomes wise and realizes that climate has changed and adjusts his planting decisions, cropping decisions, and eventually settles out here. So this is the adaptation, this difference here. This pink area are his adjustment costs in transitioning to an adapted world. And in a paper done a few years ago, we did this for U.S. agriculture, and I just have a graph here. This is a case where we look at the median county in U.S. agriculture, and it happens the median county does slightly better under climate change. And basically, we look at what happens under three different scenarios. Let me get out a pointer so I can point out this blue line. This red line here is if we don't change the climate. Things stay the same. The value of per acre, it's about half a hectare, is about $82. The value of output. If the farmer were perfectly informed, he would follow this path. This is a scenario of a slowly adjusting climate over 100 years. He would follow this pink path. And the poorly informed farmer who has to learn about the changing climate essentially takes 20 years to realize that the climate is even changing before he starts cottoning on and starts moving upwards. And this area between these two is the loss that occurs while he's learning about this changed climate. So this simple example of the farmer is really a metaphor for all of the adaptation that's going to occur by agents. None of them will actually observe the changing climate. They may think a climate change is coming. They may be pretty sure that that climate change is going to come. They may even think they know what it's going to be, but they won't actually observe, or whatever climate change they observe will be a very noisy signal of climate change, and it'll take them a while to adjust to that. And most economic agents, when they're investing money to adapt, wait to see what the changes occurred before they make those investments. Now, if you're carrying an umbrella, that's easy insurance for rain. You can also carry a sweater, but you probably don't put the sweater on until the weather is actually cooler. So the summary for adaptation is that the unobservability of climate is fundamental to this adaptation decision. Other uncertainties also exist. Costs occur, these adjustment costs, even if the firm can perfectly adapt a climate. So even if there's lots of adaptation options, there still is going to be adjustment costs as we transition to that. And risk reduction tools can be very important in reducing uncertainty and impacts. I'm out of time, so I'm going to go on to firms' mitigation decisions just in the last minute. There's firms' mitigation decisions, so we will assume that a policy has been put in place. What induces uncertainty for the firm? This is the polluter. Technological change, making a capital investment. Should I wait if the technology is changing dramatically? Should I invest in investments that are more reversible, just last a year or two instead of 10, 20 years? Markets, what's going to happen to the price of oil and how's that's going to affect my decision? Government policy uncertainty, this is a big problem. If governments keep changing the climate policy, firms are loath to make investments that depend on a policy staying in place for a long period of time. I'm going to just go to the conclusions now, but I did have some slides here on the fat tails. which Jeff talked about very well, so you're not missing anything from me. But the consequences of climate change are real and appropriate for governments. Risk management is often overlooked as a strategy for dealing with climate risk, along with mitigation and adaptation. Improving availability of measures for moderating risks can be the third leg of a climate action stool, where one leg is adaptation, one leg is mitigation, and one leg is risk moderation tools. Thanks very much.
Okay, so what do I do? I press this?
Yes.
Okay. All right, so I'm going to talk mostly about the social cost of carbon and how we might go about estimating it. It's key to climate policy. We have to get some idea as to what this number is and how do we estimate it. And the usual approach to estimating this number is to use IAMs, integrated assessment models. The interagency working group in the United States used 3 models: DICE, the PAGE model that Chris Hope developed, he's in Cambridge University, and the FUN model. And they took these 3 models and they averaged them and so on. And the typical approach is you start out with a base case path for emissions, and that leads to some base case path for GDP, all right? And then you perturb the path. You increase emissions by 1 ton today. Now, by the way, you can decrease emissions by 1 ton. You can do it either way. I'm going to look at decreases, but the way they do it is they increase emissions by 1 ton. What is that going to do? Well, that's going to cause more warming, and it's going to cause damages and lower GDP by some small amount into the future, somewhat lower path for GDP. And the social cost of carbon is just the present value of the reductions in GDP over the next 100 or whatever years. You need some discount rate to discount that, but that's basically what they do. Now, I have argued in a number of papers that IAMs are flawed. I think I used the word next to useless. And I think that's actually too moderate. I think they're worse than useless. And I want to explain very briefly why. I don't want to go over these earlier papers. And I actually want to begin by just telling you, I'm very big on modeling. I actually am a co-author of a textbook on econometrics and econometric models. So I love models. But I think that IAMs, these models, have actually been almost destructive. And let me explain why. The relationships are completely ad hoc. They're made up. And climate sensitivity, by the way, is an example of that. We don't know much about climate sensitivity. The reason we get all those different distributions is that the feedback loops are unknown. We don't even know the signs on some of those feedback loops. And what we've learned, what climate scientists have learned over the last 15 years, is they know less than they thought they knew 15 years ago. But the good example is the damage function, totally made up. Simon, who I guess had to leave, mentioned that in the DICE model, there were some estimates for 2 degrees of warming. Those aren't estimates. What happened, actually, if you read the Nordhaus book, the 2008 book on his model, he describes where he fit this inverse quadratic. How did you get the parameters for the inverse quadratic? And he said, well, from the IPCC, they said that a 3-degree increase in temperature would result in, I forgot the exact number, a 3% reduction in GDP, and a 4-degree increase in temperature would result in some other reduction in GDP. That's what the IPCC said, the 2007. So I go to the 2007 IPCC. Where did they get those numbers? From the integrated assessment models, including DICE. So it's kind of circular. So we have absolutely no data. We have absolutely no theory. We have absolutely nothing on which to base a damage function. And all right, so we make something up, but it's all made up. And the problem is that we're not straight about this, that the modelers are not straight about how made up these models are and how little we know. And these models give a sense of, scientific legitimacy, that we know more than we really do. Another problem with these models is you can get any result you want by changing the parameters. And a good example is the discount rate. So if you take the three IAMs that were used in the interagency working group in the United States to estimate the social cost of carbon, those models give slightly different answers. But if you change the discount rate, you get wildly different answers. And the problem is that the modelers can pick the parameters to get the results they want. And they then have a model that justifies their opinion about the social cost of carbon. And that's actually not very honest. So that's a problem. These models tell us nothing about catastrophic outcomes, nothing. And I'm going to show you soon that that's all that matters for the social cost of carbon, or almost all, that almost everything is driven by the possibility of catastrophic outcomes. I had an email from Chris Hope who claimed that the Page model does have it does handle catastrophic outcomes because it has a discontinuity in the damage function. But of course, the discontinuity is something he made up. It's nothing based on data. So of course, if you make up something, you can say it handles catastrophic outcomes. All right, so I've written about this elsewhere, and by the way, this applies to many models. Again, as somebody who has written a book on models, I'm very sensitive to their misuse, and I worry about actually some of the CAT models that were talked about yesterday. About how much does the user really understand what's going on, as opposed to this is a black box that we're going to take on faith. We think it's right, it's scientific, it runs on a computer. Anyhow. The problem, of course, is that since I've said that these IAMs are no good, how do we estimate the SCC? What do we do if we're not going to use this? And that's what I want to talk about today very briefly. I think in the end, we need expert opinion, and I'm going to explain this, but in a very simple way. What we want to know is what are the probabilities, so I ask you, you're experts, what are the probabilities of different economic outcomes of climate change, and in particular catastrophic outcomes, not the causes of the outcomes. I don't want the details that you think that the Antarctic ice shelf is going to collapse, or sea levels are going to rise, or this will happen, that will happen. I don't care. Just tell me, what do you think the outcome is going to be, say 50 years from now, and how much do we need to reduce emissions in order to avoid the catastrophic outcome? That's all I want. And I want to get that opinion from lots of people who study this and claim to know this. So it's very simple, very transparent. So a possible outcome might be a 20% or greater reduction in GDP. I would consider that at the catastrophic end of potential outcomes from climate change. What is the probability of that? And again, I don't care whether it's the result of very high temperatures, but a moderate impact of temperature on GDP, or moderate temperature increases, but a huge impact of those temperature increases in GDP. All I want to know is, what do you think that outcome, how likely that outcome is, all right? And what do we need to do to avert it, to prevent it? That's it. And what we're going to have is something that's extremely simple, and most important, transparent. Not going to have a big black box, very scientific, runs on a computer, very simple. Okay. So I said that the social cost of carbon is largely driven by catastrophic outcomes. How do I know that? Well, first of all, the fact is that unless you have an extremely low discount rate, the most likely scenarios in these models, they just don't generate enough damages in present value terms to matter. And actually, that's why the interagency working group in the United States, using a 3% discount rate, got an estimate of the SCC of about $33 per ton. They've since raised that a few dollars, but about $33 a ton. That's a very low number, by the way. It would generate enough money barely to pay for the food at the Paris Climate Conference. So this is a really small number. But they got that number because they're using a 3% discount rate, and you have all these middle-of-the-road scenarios. We can show you, I don't know if I'll have time today, but with simple examples that low probability but severe outcomes will always dominate the estimate of the social cost of carbon. And what do we mean by a catastrophic outcome? Is it a high temperature? That's what climate scientists usually mean. That's very hard to know. What matters is really not the temperature increase. What we care about is the impact. What is it going to do to the GDP? And when I say GDP, I'm including things like species extinction, increased morbidity, increased mortality, monetizing all of those things, and including them in a measure of GDP. That's what matters, the impact. So, what is the approach? And you may say I'm using a model. In some sense I am, but it's extremely simple and transparent. So the primary object of analysis is the economic impact of climate change. And I don't care about the mechanisms that generate that impact, only the outcomes. And I'm going to focus on percentage reductions in GDP that are large, 10% or more. The bad outcomes. And I want the probabilities of these under business as usual. So let's take this pessimistic view that nothing's going to happen in Paris, that there isn't going to be an agreement in the next 5 years or 10 years. We're going to have business as usual. We want to know what are the probabilities of these really bad outcomes, and then we're going to use opinions for this, expert opinion, and then by how much do we need to reduce emissions in order to avoid some of those outcomes? Let's say avoid the 20% or more drop in GDP. What would it take? So here's a hypothetical expert. These are just numbers I wrote down. So here I'm the hypothetical expert. And in the top half of the table here, this is an opinion about 50 years from now. What is the likelihood of different percentage reductions in GDP? That's Z. So we're going to assume that there's no chance that nothing will happen. There's at least a 50% chance of a 2% or greater impact, a 10% chance of a 4% or greater, 6% of 10% drop in GDP, 5% chance of a 20% or more drop, and a 4% chance of a 50%, that's a big drop in GDP, and no chance of a 70% here. I'll get to this 150 years later, but for now, this is what I get from this expert, from this hypothetical expert. Now, I want to get this from many experts, from 100 experts or more, because then I can fit a distribution to this. But for now, we have one expert here, okay? And we're going to fit a distribution, not to, let me go back up here, not to Z, but we want to fit it to phi, this parameter phi, which is the negative of the log of 1 minus Z. The percentage drop in GDP you can think of as e to the minus phi times GDP. And the reason we're going to do that is that phi is unbounded. So we can fit a thick-tailed, fat-tailed distribution to this. We go out past 1 to any large number. So we're going to fit a distribution to phi. An example would be the generalized Pareto distribution. This is a fat-tailed distribution. We can fit this. The parameter alpha determines the fatness of the tail. If alpha is greater than n, it means the first n moments exist. So the smaller is alpha, the fatter is the tail. And for the numbers that I just showed you in that table, it turns out that alpha is about 0.76, theta is close to 0, and k is about 0.03. That's how you'd fit this thing to that data. We can do this for a whole set of expert opinions, a whole set of numbers, all right? And we can also do other distributions. We can say, look, let's try a thin-tailed distribution, a displaced gamma distribution, or a generalized extreme value type 2, Frechet distribution, which is also fat-tailed. And then we can compare these and see which distribution gives the best fit, and then use the distribution to determine, well, what is the probability of a catastrophic outcome, and then what is it going to take to avert that outcome, okay? So we begin with a scenario for the objective of some abatement policy. Let's say we're going to truncate the tail of the impact distribution so that we don't experience an outcome in 50 years where GDP falls by 20% or more. And B0 is the present value of the expected avoided reduction in that flow of GDP. This is in dollars. And delta E is the change, the cost measured in terms of the total required emission reduction, the total amount of emissions that we're going to have to do away with in order to achieve B0. And then the social cost of carbon is very simple. It's B0 divided by this delta E. It's the total benefit in dollars divided by the total number of tons of CO2 that we have to avoid emitting. Very simple. It's dollars per ton. And all we need to do is estimate B0 and delta E. And I want to point out, I'll come back to this if there's time, this is an average social cost of carbon. It's not a marginal one. In economics, we usually think of a marginal measure. In fact, that's what's done with these integrated assessment models. If we have one more ton of carbon emitted, what is that going to do? How much is that going to reduce GDP over time? Or one less ton, how much do we save over time? This is an average number, and we have to think about what the difference is, what it means, which I'll get to. Now, what I'm going to do here is assume that under business as usual, we start out with no damage. This is the way the reduction in GDP works. At time 0, beta t is 0, so that's z sub t is 0 at the beginning, and it gradually approaches asymptotically the value zm. That's the maximum reduction in GDP over a very, very long time horizon. And what we want to do is calibrate these two numbers, these two parameters, zm and beta. Beta is just the rate at which we approach this maximum. And if we have an average outcome, average expected reduction for two horizons, T1 and T2, then we can very easily determine beta. So that's why in the table I showed you before, I also had 150 years. What would be the average reduction in 150 years? And in that table, the average reduction in 50 years was 5% GDP, and the average reduction in 150 years was a 10% drop in GDP. This is this expert, hypothetical expert, all right? And with those numbers, it means that ZT is the Z2 over Z1, the average number is 2, it gives you a beta of about 0.01, roughly 0.01. So we need to also ask these experts, well, what do you think is going to happen in 100 or 150 years? And then we get a number for beta. And now, this is the worst math you'll see, but it's really, we're going to treat this maximum as stochastic, and I'm going to use the distribution for 50 years from now that we got from these experts, all right? Well, what is the benefit of eliminating 20% or greater? It's the expected value of the final reduction in GDP for the full distribution minus the expected value of the truncated distribution, getting rid of the first outcomes. And all we're doing here is taking account of the gradual growth in the reduction in GDP. We're discounting at a rate R, and we're assuming that GDP grows at a rate G. If there's no climate change, it'll grow at, let's say, 2% a year. And that gives us the benefit, all right? So basically, we need to know the difference in these two expectations. What about the emission reduction that we need? Well, we know what current emissions are, and we're going to assume that under business as usual, they're going to keep growing at some rate, m. And let's suppose that we need to reduce emissions, and that by reducing emissions by some fraction psi 1, the entire path of emissions, now through the future, suppose that would be enough, according to the experts, to truncate the distribution, get rid of those worst outcomes? Well, then we know what the total change in emissions is. As long as the real cost per ton is constant, per ton abated, we use the same discount rate that we use to discount changes in GDP, and it's very simple. We're going to get that the total amount of emissions that need to be avoided is this percent, which we get from experts, times current emissions divided by discount rate R minus M. That's it. And so here's an example, a numerical example. We'll take data for 2013, and we'll rely on this hypothetical expert. So world emissions, GHG emissions, equivalent CO2 emissions, were about 33 billion metric tons. The average growth rate over the previous 14, 15 years was about 3% for the world, although for the US and Europe it was roughly zero, no growth over those last 14 years. All the growth was due to Asia, and it's likely to slow even without any agreement simply because it's getting hard to breathe in China and India. So I'm going to set M to be about 2%. In other words, if we don't do anything, emissions will grow at 2%. World GDP is about 75 trillion in 2013. The average growth rate has been about, per capita, about 2%, real growth rate. I'm going to use a 4% discount rate, and I just showed you that based on that hypothetical expert, beta is about 0.01. All right? Let's suppose that if we cut emissions by 30%, we can avoid those two worst outcomes. We can truncate the distribution. All right? So if you truncate the distribution, the expected reduction in GDP is only about 2%. If you don't truncate it, it's about 5%. That says that the benefit is going to be roughly $89 trillion in present value terms. What about the emission reduction? It's going to be about 510 billion metric tons of CO2 equivalent. You divide one by the other, and it gives you a social cost of carbon. With this example, it's $175 per ton. Okay. Now, we can do this for other cuts. Suppose we want to get rid of any impact. This is probably not realistic, but you could come up with a number and get a different social cost of carbon. All right. The reason the catastrophic outcomes are what matter, if you look at that hypothetical expert, you know, most of the percentage reduction comes from the tail. If you get rid of the tail, you've gotten rid of 60% of the damage. So usually what's going to happen is the tail that's going to matter. All right, I'm going to move quickly here because I'm running out of time. All right, this is normally you have a marginal SCC. This is an average one, and we're looking at a large change in emissions and a large benefit. But this is actually consistent with the way we think about policy. We want to have an agreement that's going to make a big difference. So we're looking at the benefit of that big difference and the cost of that big difference. So here, the social cost of carbon measured as on an average basis actually makes sense. We have to keep in mind that it may differ from the marginal social cost of carbon. Here's the questionnaire. I haven't done this yet, but I'm hoping to do this, and if you have suggestions, I'd love to hear them. So the questionnaire might be this. Suppose nothing is done to reduce greenhouse gas emissions. What is the probability that in 40 or 50 years from now, the climate change that results will cause a reduction in GDP, world GDP, of 1% or more, 5% or more, and so on, 20% or more, 50% or more? What are those probabilities? Those are the first questions. And we want this to be a very simple questionnaire. Again, nothing's done. What's the probability that 100 years from now, climate change will cause a reduction in GDP of 1%, 5%, and so on? What are those probabilities? Let's go back to the 40, 50-year horizon. By what percentage would worldwide emissions have to be reduced now and throughout the future to avoid a climate-induced reduction in world GDP of 20% or more? By how much would we have to reduce emissions? So I'm not looking for very much information here. This is very, very simple. And I don't care how people get these answers. So one expert might have used an integrated assessment model to get these numbers. That's okay. Some other expert might have used something he or she learned about something, or a book they read, or whatever. That's okay. All I want to know is, what do the people who work on this think is going to happen? That's it. I want to have a summary of what everybody out there who's serious about this and thinks about this, what they think. And then I want to take that summary, what they think, and I'm going to use that to come up with an SCC estimate. They may use models, they may use something else, but I want something that's extremely transparent, that there's no hocus pocus, there's no black box run on a computer with all kinds of complicated stuff that nobody understands. Very, very simple, okay? All right, so how do we estimate the social cost of carbon if we don't use an integrated assessment model? And I don't think we should use integrated assessment models. I think we can rely on so-called expert opinion to obtain these probabilities and to obtain, that way get the benefit of reducing emissions, and also to estimate the reduction in emissions that would be needed to avoid some part of the possible distribution of outcomes. And that gives you a total emission reduction, and the ratio of these two things gives you a very simple measure of the social cost of carbon. That's it.
Any question?
Hi, Fad Nias from RMS. I'm actually sort of building and selling models to the insurance industry, and I think some of them are actually useful, although I really agree with many of the statements the last speaker has made. I have also worked a long time bridging the gap between physical science and the economy in the context, or economists in the context of climate change policy design. And I want to make sort of a couple of comments with regards to the first two speakers. And I believe they are important. They might be a little philosophical, but I feel they are really important. So the first point is sort of this climate sensitivity distribution we are sort of looking at, like in the first two talks. It was quite a central sort of piece. So that equilibrium climate sensitivity is something which is an oversimplification of the physical system. It was used in the very beginning where climate models actually had CO2 as a constant. And that's why equilibrium climate sensitivity is always assumed. But in reality, from a system theoretical viewpoint, the climate system is never a conservative, equilibrated system. It's constantly transient. So we don't have a sort of zero energy balance, and we never will. So the assumption of equilibrium climate sensitivity is sort of a weird thing. It doesn't even exist in the real world. Professor Hill, you said, like, well, it is not a distribution, it's a real deterministic number. It's not. It has nothing to do with the physical climate system. It doesn't exist in that system. So that's my first comment, which is really important because, like, when you think that through, you take that distribution, which should be a number, but it's a distribution and a number for climate models. And then you apply a Bayesian framework to infer something on the real world economy. I feel there's something sort of missing there, and I believe it's sort of a time lag of the integrated assessment model being sort of the tool of choice, and that is sort of a questionable choice maybe. But the integrated assessment models are built on the assumption that there is something like a climate sensitivity, because at the time when the integrated assessment models were sort of invented, climate sensitivity was the tool to look at. And that's the bridge, to kind of take the physical science and couple it with sort of economic models. But this bridge is based on something which doesn't even exist in the physical sort of system, which is basically based on the rate of change, all the feedback mechanisms which are sort of triggered to actually lead to the impact are not incorporated in that equilibrium climate sensitivity. And it shouldn't be confused with what we know about climate change. When you look at that distribution,
Sorry,
I think
we have limit time, so can you...
Right? It's not what we know about climate change, we know much more about climate change than we know about that climate sensitivity.
Thank you.
Just a very quick response. Yeah, I think a lot of what you say is correct. The most climate scientists at the cutting edge have replaced discussion of equilibrium climate sensitivity by a more complicated concept at this point. It's a measure of transient rather than equilibrium response. But it's still a focus of a lot of discussion within the IPCC context and so on. I think it's true that most IAMs use this, and I think nobody on this panel is going to support the current generation of integrated assessment models. I think all three of us are rather negative about the current structure of integrated assessment models. So I think that's one of many criticisms you can make of integrated assessment models. Probably not the most important criticism you can make of them. I think the most important criticism you can make of them is the one that Bob made, which is that the damage functions are essentially arbitrary. And given that, the rest is sort of almost irrelevant. I was using the equilibrium climate sensitivity merely just to give you some sense of the nature of the uncertainty and the extent of the uncertainty. If I'd given you the transient climate response data, first of all, there's actually much less study of the transient climate responses, so I couldn't have drawn that same diagram for those. So the uncertainty in that case would have been considerably larger, actually. But I was using that basic data basically to make a point about the extent of uncertainty about one of the most widely studied parameters in this business.
Erwan Michel Cajon, the Wharton School. That's a question for you, Bob. On the one hand, I like the proposal of being more transparent, no question about that. On the other hand, I'm ready to question what the robustness of the result of asking people what they think about that very question will be. And I don't know what you expect to get out of it in terms of robustness of these estimates, whether it's asking them confidence interval into their estimate, whether you want to even ask willingness to pay for that abandonment, or whether you just get that number as is and make it your main parameter in your model. How do you treat that in terms of making sure that the right number, so to speak?
Well, first of all, I'm not going to ask for a confidence interval because I'm asking for probabilities of different outcomes. So, I would ask you as an expert, I would say, what do you think the probability is, the chances that in 50 years there'll be a 5% drop in GDP or a 10% drop? So you're going to give me some numbers, and then to the extent there's a confidence interval is only through, there's a whole variety of experts, a whole lot of people. I'm not going to ask about willingness to pay. That's a complicated concept. All I'm going to ask about is what do you think the probability is of several possible outcomes, and what do you think it would take to avoid some of those outcomes, some of the worst ones? That's it. Very, very simple. And I expect to get a big range of answers. I think there's a lot of disagreement. That's okay. I just think this is a simpler, more transparent, and in some ways more honest way to go about thinking about the social cost of carbon than taking some big complicated models that nobody understands and running them.
But don't you care, I know we're running out of them, don't you care about how certain they are about their distribution? You don't?
No, because I'm going to get that by looking across many people. So just give me your best estimate. And it'll differ from, Christian will maybe give me a different estimate. And we'll get a sense of the uncertainty that way.
But you're going to weight them the same way?
Oh, Christian's more because
no, I was going to suggest that, of course.
No, I'm kidding. I would probably weight them all the same.
Charlie, you want to add something?
Yeah, I just wanted to pose a question to Bob. Many of us were probably thinking, how am I going to answer that when I get that questionnaire?
You will.
If the main problem is damage, then why not focus on that component of it? Or if there are lots of components that are problematic, why not break the thing down into more digestible pieces rather than asking for a grand summary, which is really tough?
Yeah. I think the reason is that it's actually too tough to ask for pieces. And, to the extent that if it turns out that nobody has any idea what the chance is of a drop in GDP, of an economic impact, that's like saying we know nothing about climate change. We don't know anything. So first of all, let's get rid of the models, because we've already agreed we don't know anything, so there's nothing in the models. And, what we're going to do is just come up with some carbon tax or whatever as an insurance policy based on some putting our thumb in the air, just some rough idea. So I actually think it makes sense to kind of start with the bottom line. Do you think there's a problem with climate change? Do you think something's going to happen? If there's no agreement, if nothing's done, if we have business as usual, what do you think the world's going to look like in terms of how much lower GDP would be? And whatever it is that goes through your mind to get to that answer is fine. That's what we know. That's what we think. And from that, it implies some kind of social cost of carbon.
Yes. I have one question to Jeffrey and one remark to Bob. I was quite impressed by the density functions that you call the purple one. Extremely scary, non-Gaussian. And my question is, what type of model produces such a density function where the probability to have 8 degrees increase of temperature is higher than to have 6% and lower than to get 2%? That's very strange to me anyway. And it did attract my attention because all the other density functions are, let's say, Gaussian. And the question to Bob, we had an issue at SCOR when we built the internal model to assess solvency under Solvency II. And the idea was also to extract expert judgments, because it was to find a correlation between GDP change on one side and the appearance of risk in property or liability or whatever. And so we developed a tool to extract expert judgment, so I have to try to see what's in the black box of the mind instead of developing, I don't know, an econometric model to find correlations. And with Michel Dacornia, that's called Probex. It has been published. Maybe if you could, Michel, say a few words on Probex, it would be certainly interesting, because that's exactly what we have done and what you propose to evaluate as social cost of carbon. So anyway, Jeffrey, I don't know, what's the purple line density function?
That's a good question. I'm not actually, I don't think I can answer it, unfortunately. I can give some relevant information, but not much. It's not totally clear why the models differ in the ways they do, and one of the whole points of that project, the Climate Model Into Comparison project, was to try to understand better which aspects of the model drive the differences in the shapes of those PDFs. The only thing I think I can say, which is sort of vaguely relevant, is that the right-hand tails of those distributions are much less well constrained by the data than the left-hand tails. The climate so far has increased, the temperature, global mean surface temperature has increased by about 1 degree, roughly speaking. So we have some data on the left-hand tail. And the data on which the models are calibrated obviously includes that. So you'd expect more agreement on the left-hand tail than you would on the right-hand tails. The right-hand tails are talking about temperature levels which have never been attained anywhere remotely like the historical record, even including sort of carbon traces and so on. So they're much less constrained by data and much more reflective of differences in the technical specifications of the models. So there's an argument you shouldn't take too much notice of them, but on the other hand, they are the best information that we have at this point. And presumably they are essentially reflecting the judgments of the individuals running the models, to go back to Bob's way of approaching things.
Short question, please.
Shan Wang from Geneva Association. I have a very simple question. Why are you measuring damage using in terms of GDP? Because for ordinary people, it's really, the damage is something tangible, whether it's a natural disaster, it's a pollution. What I'm trying to say is that, if you damage the environment and then trying to fix it, that may generate GDP numbers. So maybe we need another measure of damage. Thank you.
Absolutely. You could argue that if a species goes extinct, it won't show up in GDP. If some caterpillar becomes extinct, it won't show up in GDP, but it's a damage. And there are ways, environmental economists have ways of valuing those things, of putting values on them. There's a lot of disagreement about how it should be done, but it can be done. The problem is that if you're going to try to get a social cost of carbon, the word cost means dollars or euros or something. In the end, you need something that measures things in dollars. So you have to somehow translate these other impacts, social disruption, people having to move, political problems, whatever it is, you have to somehow put it in monetary terms. Otherwise, you can't think about a carbon tax.
Okay, 3 last quick questions. So 1, Georges? Or Christian, okay, Christian, go.
Okay. Sorry, George. Thank you. One quick question. I think we talk a lot this morning about disagreement between experts and ambiguity. I mean, one expert not knowing what's the true distribution or something like that. Jeff suggested the use of a specific decision process where we take more, we put more weight to the more pessimistic expert. I would like to hear Bob on this, whether he agree using something like, ambiguity aversion concept to aggregate the position of or the belief of the different experts.
Well, I may not understand ambiguity aversion as completely, but to me it's take a utility function and then put another function over it that creates the ambiguity. And that other function, the problem is that other function is kind of arbitrary. So I don't quite see what we gain by doing that. In fact, that's why I'm sort of moving away from willingness to pay, because willingness to pay requires a utility function. And on the other hand, the social cost of carbon can be measured simply in terms of just pick a discount rate and what's the present value of the avoided GDP loss. So you don't have to get into utility functions, never mind ambiguity functions.
Professor Pindijk, what is your definition of an expert? Okay. And second, how will you build up your sample? Will it be academics, economists, physicians, farmers?
Well, probably not farmers.
No?
No. No, look, I haven't gotten that far, and I don't know how I'm going to build up this. I would love advice. I mean, I think it would include economists who, not all economists, but people who study this, climate scientists who study this, environmentalists who study this, maybe people in the insurance business who study this. That's it. I mean, I want to survey those people who have opinions. There are most farmers probably don't have opinions about this, and get as wide, a group as I can. But I haven't given that a lot of careful thought yet. I'm not at that stage.
Just a few words on Probex, which is exactly this. Probex, the method we have developed at SCOR that Denis was talking about, is exactly for this. The problem we have when we build our internal model is to know what's going to happen in the extreme. Already extreme by definition there are very few, and dependence between few variables is almost impossible to calibrate. So the idea was to use what we call a Bayesian method, mixing prior information that we have, observation that we could have. Some, you said, there are some observation on the right side of the distribution, and expert opinion. Mm-hmm. And so we did that at SCOR for calibrating our copulas for the risk. And it turns out to be a very rich experience, very interesting, but dangerous. That's why I liked the comment of Professor Dion. You have to carefully select your experts, and you also have to make sure that you have a good, what the jargon is, elicitation process. Because the way you ask the question, you can get bias in the answer. But a note of optimism, we did it, and we got very interesting answers. So we have published a paper in Astin Bulletin. If you're interested, I
would like to see that. Yeah.
Give it to you. I let you go for lunch. Thank you.
Okay, so thank you very much, and let me remind you that we start at 1:30, not 2 like yesterday. So it's 1:30. So we have just a bit more than 1 hour to have lunch. Thank you very much.